Hello, everyone, and welcome to Lattice Security Seminar about Trusted Platform Modules, or TPM for short, and FPGAs, and why are they needed in secure systems. During this seminar, we will hear from our distinguished panelists about how TPMs are evolving and how they can complement Root of Trust FPGAs and why this combination is becoming essential for building resilient and future-ready systems. So let's get started with the introductions. I'm your host, Mamta Gupta, AVP Marketing at Lattice, leading security, data center, and telecommunication business segments. 20 plus years of experience in FPGAs, mostly in aerospace and defense and high fidelity projects. I came to Lattice about 6 years ago, and since then have been leading these segments. I will now turn over to our panel of experts and have them introduce themselves. Eric, why don't you kick us off?
Thanks, Mamta. So my name is Eric Sivertson. I'm the Vice President of Security Business at Lattice. And I started about the same time with Mamta. She and I have done a lot of this work in security at Lattice together. Prior to that, I have, hate to admit it, 30 plus years in security, originally starting in military, aerospace, defense, intelligence community work, moving through to even having my own consultancy. And I'm currently the Trusted Computing Group representative for Lattice on the TPM work group. Over to you, Ari.
Thanks, Eric. Hello, everyone. My name is Ari Singer. I've been a security architect and designer of security solutions for over 25 years, so almost up there with you, Eric. I played a key role in technology development and contributing to writing standards in public key cryptography, secure wireless networking, and trusted computing, serving as chair of the IEEE P1363 working group, as well as the TCG's TPM and TSS work groups. Since co-founding Trustify in 2014, I have helped organizations bring next generation security technologies to market. Trustify is a security services and software development company that helps technology companies design and develop security into their products and systems. And it's great to be here. Over to you, Steve.
Yeah, hi, my name is Steve Clark. I'm a security technologist with CLSQ. Just give you a background on CLSQ. We've been doing secure semiconductors and secure PKI for over 25 years. I've been with them for going on 10 years now. My background is actually optical engineering. I've been in the industry for 35 years, started in the defense sector, and have moved over to secure semiconductors about 20 years ago. And I've been working with secure semiconductors. I've been involved with many standardization organizations, including Open Connectivity Foundation, USB Type 3, Industrial Internet Consortium, and now I'm representing CLSQ for the at the TCG for the TPM standards work groups as well. Glad to be here.
Welcome. Yeah, welcome, panelists. Now let's get into the meat of the things. And my first question to all of the panelists is, what is a TPM? Let's lay it out for our users. What is a TPM? How is it used in a system? And let's get the introduction done about this topic. So Ari, let's kick it off with you.
Sure. So the TPM is a standard for a hardware chip that goes deep into your computer or device to help ensure that it is running what it's supposed to be running, right? So it's all about saying, can I trust this device? And it's part of your system. It protects keys just like any other kind of security module. So it was invented in the late 90s and the newer versions in the early to mid 2000s. So following after smart cards and those things, It's a security module with cryptographic keys and all of that. But in addition, it has built-in capabilities to measure and report the state of your platform. And it serves as sort of a root of trust, which I think we'll talk about a little bit later. Steve, you want to add to that?
Sure. So one of the things that you mentioned was the storage of keys, and just so everyone's clear, it not only stores keys, it actually is a crypto coprocessor. It actually uses the private keys on chip so that the keys never have to leave and they're always secured on chip. So for example, if you wanted to do a sign operation that requires a private key, you would send the public data over to the TPM. It would return the signature, but internally, it would use the private key that's stored internally along with the crypto algorithm that's appropriate to do the signature. So it serves as a key storage and crypto coprocessor, both of those functionalities.
I'm happy to chip in too. I think you guys covered a lot of it. One thing that I don't think we hit much on is the integrity measurement. So a really important part of TPM is being able to do the firmware attestation, if you will, and the bootload process securely. So measuring a system to know that it's the right system and storing that information in what they call platform configuration registers, or PCRs. And that gets used multiple times by the system for attesting that it is something you can continue to trust, not only to trust the boot, but you can continue to trust it. And another very important aspect of the TPM is providing a great source of entropy, or random numbers. So this is another feature that you get with TPM, which is critical whenever you're basically doing ephemeral keys for, channel management and things of that nature. And then the last point I'd make, and Ari touched on it, it's built by the Trusted Computing Group, or the spec is defined by the Trusted Computing Group, and they are celebrating over 25 years of the TPM. And that group is made up of a lot of major players in the industry. Google's a part of it, Microsoft is a part of it, Lattice is there, CLSQ is there, Ari chaired it. But it's all done by industry. This is not a government standard. This is where the leaders in the industry came together to define this spec and evolve this spec over 25 plus years now. So those are some other points I think are important as to what a TPM is.
Okay, no, that's a great overview. Now, I always hear, and I think you all alluded it too, there's always this concept of root of trust. So I would like our panelists to weigh in on, or at least educate us about what is a root of trust and how does it relate to TPM. And I would again start with Ari. So Ari, how about that?
Sure. Yeah. So, there are lots of different kinds of roots of trust, but fundamentally, when you talk about a root of trust, it's something that's at the foundation of your system that you have to assume is good. If that thing isn't good, all bets are off. So, the first thing is a root of trust has to be well protected and sort of a core part of your system. So when TPMs came into existence, it sort of crystallized in the commercial world a lot of the stuff that had been going on in government spaces. And it sort of defined, there were 5 initial roots of trust. And if people want to look it up, it's NIST Special Publication 800-164. But the 5 roots of trust are for storage, protecting keys, integrity, reporting, measurement, and verification. And so TPM was designed to cover 3 out of those 5. So it was designed to store the integrity measurements and be able to, as Eric said, to attest to the state of your platform to the outside world, as well as enforce some access control based on that state. And also, as Steve was talking about, storing those private keys. And, as time goes on, there are other roots of trust that have been defined around cyber resilience and all that, and maybe we'll talk about that later as well. Eric, you want to add to that?
Yeah, no, I think this is something I talk to a lot of customers about. If you think of the TPM in terms of static and dynamic type of capabilities, um, the TPM I really think was a root of trust designed to be a little bit more in a static capacity with those three measurements you talked about. And so if you think of security, going back to World War II, because that was the beginning of electronics tied to this stuff, you have kind of what's called a castle model, where um, it's thought that everything has a very defined perimeter and the access to the castle is key. And so the TPM was kind of like the credential storage and the integrity measure of the castle, if you will. So for that capability, it's excellent, and it was purpose built for that. But now, as we've evolved, we're getting into a much more of a not a castle model, but a distributed model. The wireless standards and the proliferation of the internet really have opened up the perimeter such that it's very hard to define that anymore. And you need to be more dynamic. And so the concept of cyber resilience, and we're going to, Ari, you touched on that. We're going to talk on it again in a little bit. That this is really where, and we're going to have a deeper discussion. I think Mamta's got a question on this later, where the TPM is good as that credential store, but for dynamic detection of attack, it's not really purpose built for that. So from a root of trust, you want to have both. Even if the credential store is impenetrable, if you can't use it when you need it, you get denied service. It's hard to call it a root of trust for your entire system. And so, Steve, you want to add to that? I think.
Yeah, sure. There's a little bit of an overload of the terminology root of trust in the industry. There's the platform root of trust, which is the TPM, which includes the measurement of the firmware that's on it, and it includes the storage and reporting and all of those things that are platform related. There's also the PKI root of trust, which is also a terminology that shouldn't be confused with it, which is the certificate authorities that you would have that would provide the infrastructure root of trust. A PKI is public key infrastructure roots of trust would be the certificate authorities, and the private keys that are and Eric alluded to this point as well. The credentials that are required are actually certificates, and those certificates need to be signed usually using a PKI kind of a public key infrastructure mechanism that provides a third-party assurance that yes, indeed, this is for this infrastructure that root of trust is trusted. So that's a different aspect of it.
Yeah, small word or small phrase, root of trust, but it has so many implications and meanings, and it relates to so many different functions and aspects of a secure system. Now, thank you, panelists, for taking us through that, very comprehensive description. So now that we have established, the introduction of a TPM and a root of trust, now why do we care? Why should system designers care about it? Why should our customers care about these things? So I would start with you, Steve, for us to take us through this. That why should we care?
So basically, what you can achieve with a TPM is a secure identity. You can achieve also secure communications, and you can achieve data integrity. So these are three very important security properties that are applicable to, I would say, most security use cases. And the secure identity, secure communication, and data integrity, that is why the TPM is important in the marketplace. And it, in general, I've said this already, but it provides those resources for achieving those security attributes as a crypto coprocessor. So it takes the load off of your primary processors, so that they don't have to. So cryptography implementations are usually very heavy, and they are resource heavy, and in terms of both processor memory and processor performance. So the TPM can be a crypto coprocessor and remove some of that requirements and burden off of the main processor.
And Steve, also, I think
Ari?
yeah, actually, so what I was going to say, I think also, Steve, what you're also pointing out that's important is whenever anyone designs a crypto system inside their chip, that's a high risk endeavor because you've got to get everything right. And with the TPM having it as standardized, that's another benefit to having a coprocessor consistent.
Yeah.
Maybe Ari, you want to jump in?
Sure, yeah. I mean, right. So, I mean, the reason you care about TPM, or we care about TPM, is it represented a fundamental shift in the way security in commercial systems was thought about, right? As you mentioned, it was standardized. All of the major PC vendors, as well as Microsoft and Intel, kind of got together and said, this is how it's supposed to be done, right? And so now you get to a point where you're not saying just, well, which system is this, but can I trust this system? Is it behaving the way it's supposed to be? And it's good for device management. So, what am I running? Am I running the correct firmware? Am I running the correct software? Eric, did you want to add anything else?
Yeah, Ari and Steve, all good points. I think another very important point and why you should care about TPM is the classic installed software base. There's gazillions of lines of code at the system level, and thanks to Microsoft requiring TPM now for all systems that run Windows 11, there's quite an installed code base out there to support the TPM. So I think that's another reason why people should care. For any systems that need to use those services, it's good to have the TPM capability on hand. And that can be done both with a standalone or soft TPM. And I think, Mamta, we're going to talk about that with the FPGA coming up as well.
So that brings us to a very related topic of use cases. What are the common use cases for TPMs? So you all touched on that a little bit, but I would like to now list out some concrete use cases. How are they typically deployed? And Steve, why don't you start us off on that?
Sure. So the TPM is focused on platform security, as we've already discussed, and the first use case of the TPM was the PC, which so it measures the BIOS, it measures all the whole stack up through the OS so that you can trust the any application that's actually running. So the PC is kind of the first use case, but it's expanded since then into secure storage and IoT, networking and trusted nodes, as well as security cameras and many other use cases. Also, there has been integration with TLS connections, and you'll see this integration with, like, for example, Wolf SSL or OpenSSL have done integrations for their TLS connections, so that their certificates are stored on the TPM, as well as the private keys, and they perform all of the cryptography is performed on the TPM, but it's called into all the cryptography required for a TLS connection is performed on the TPM, and that TLS connection is established through the Wolf SSL stack, for example.
Thanks, Steve. Yeah, so in terms of use cases for TPM, we've seen TPMs implemented in a variety of places. So protecting election systems, obviously you want to make sure those don't have any problems. Hardening systems for government use. So for instance, putting it in ruggedized devices that go out in tanks. You obviously can't just bring those in and get them repaired anytime. So they really have to be well protected and secure. There's a lot of work done related to supply chain validation. For instance, Intel has done some things there where when you get your system, there's a bunch of information about what what's in your machine, but also you can verify in the field at that moment is the correct TPM on there, so it's actually a valid machine. And then I think, as we've been alluding to, Microsoft has it as a requirement. They use it in Windows systems. And early on, one of the key use cases was drive encryption, so that an attacker couldn't boot into Linux and change the Windows password or something. So you can't do that anymore because it's encrypted.
Yeah.
Eric, did you want to add something on that?
Yeah, so I'm going to go back to my discussion on that castle model. I think what's happening in the industrial space is very interesting. You will find that for industrial single board computers, let's call it sensor aggregation hubs, things of that nature, especially as more AI comes into the industrial world. Humanoids really are a moving, industrial robot that now is going to interact with us. Because of the networking of all these devices, that segment is now starting to really pick up and use the TPM for that identity, the credentialing, and the attestation. So I think you're going to see building of that use case in the industrial segment quite a bit. Again, at the single board compute level, they're already doing it, but I think it's going to spread in more parts of the system.
Okay, those were very interesting use cases, and always good to hear about non-data center, non-single board computer, election machine systems, battle tanks. What else could be more interesting? But as I study systems in data centers and telecommunication, I always see our root of trust FPGA sitting right next to a TPM. So I want to go back to the point that Ari brought out about 5 kinds of roots of trust. I don't know if many of our viewers comprehend that there are indeed many kinds of roots of trust. So I would like to bring up a question here: that how do TPMs and FPGAs work together? And if someone were to implement a TPM inside of FPGA, how would that work, or how would you decide whether you need a standalone TPM, a standalone root of trust, or a combo of both? So Ari, I would begin with you because you brought up that very interesting thing about 5 kinds of roots of trust. So how do these 2 roots of trust play together?
Yeah, I mean, that's a really, really important question. And FPGA is a great technology to use with TPM or to build a TPM into. And the reason it does come back to those 5 roots of trust. So, an important thing to understand about TPM is that it cannot and does not, at least in its historical form, work by itself. It's part of a bigger system, right? So, the critical thing on PCs that was always needed was the root of trust for measurement. So that first thing that boots up is before the TPM, and it just tells the TPM, hey, here's who I am. And so you really need that, root of trust for measurement. And similarly, secure boot is something that historically TPM can't do at all, right? So you do your secure boot, you verify everything, and then the TPM kind of supports you after that. So, one of the great things about FPGAs is they have the ability to be that first thing that's running, to measure the first thing. And so, you've already solved a lot of the problems that are needed to go in conjunction with TPM. So it's sort of a great way to integrate all of those roots of trust into one. And another good thing, obviously, is that you can add new features over time.
So, Ari, yeah, I think to borrow one of my favorite analogies and one of my favorite candies, it's like chocolate and peanut butter. Separate, they're good, but when you put them together and get a Reese's peanut butter cup, it's delicious. So, I do think that your use case is a very good one, that secure boot. And I'm going to go back to something I talked about earlier, which is cyber resilience. That ability, not only after your system is securely up and running, credentialed, attested, but how do I keep bad guys out? How do I watch for that? How do I protect the system from that? And Mamta, you know this well. This is something you and I did a lot on early days, protecting data centers with PFR, platform firmware resiliency. So being able to monitor things like I2C, SPY, I3C in real time to catch attacks before they can do any damage. FPGA is fantastic for that. TPM was not built for that. It's not its purpose, as we've discussed. So when you put the two together, now you have all that legacy software that can easily integrate, but we also now can provide this great extra sets of protection. And then we can also protect the TPM a little better than when it stands alone. So those are some of the other great benefits. Steve, you want to add to this?
Yeah, sure. I think one of the things that relate back to the use cases, and so there are many use cases where a standalone TPM is perfectly adequate to provide your security. We're talking about the PC booting process, a trusted platform for storage and for security cameras and IoT. But there are also use cases which Eric just pointed out, where the cyber resilience is an important factor. And while the TPM can provide the crypto algorithms and the crypto security, the FPGA is able to provide the other kinds of security that you're going to need, as Eric has pointed out, the communications or there are other attacks that it can respond to in real time. So there's also so that gives a flexible implementation for the pairing of the TPM with the FPGA for higher performance applications. There's also a chiplet kind of an application where if you pair both the TPM and the FPGA, it can be an element in a chiplet element in a system on chip SoC that might be able to just provide the extra security in a package that can be reused in a SoC context. So those are a couple other places that FPGA and TPM work together.
Absolutely. You guys described it perfectly. This is what we see day in and day out, our data center telecommunication customers adopting, that combination of, a secure boot, root of trust of measurement, implemented in FPGA, but a key box and anti-tamper could be, on the TPM. And so thank you for that. Now, one question that is coming up a lot of times now is about post-quantum cryptography. Whenever we have any discussion about security, this is now on everybody's mind. That is my system compliant with the post-quantum cryptography regulations that are coming up, or is my root of trust compliant? So I want to now bring it in with respect to the TPMs. How is post-quantum cryptography going to impact TPMs? And Steve, why don't you lead us into that?
So as you said, the PQC will be on us soon. And so I'd like to talk about the schedule and what the PQC is going to be introduced as. So the Commercial National Security Algorithm Suite, or CNSA 2.0, has already been defined for which PQC algorithms that are going to be initially what are going to be rolled out. And the Committee on National Security Systems, or CNSS, Policy 15, CNSSP 15, actually provides some of the guidelines of how it's going to be rolled out in the national security systems. And we could use that as a guideline for normal rollouts for other. But the point here is that PQC is already upon us, and it's going to compromise ECC communications. It's going to compromise RSA communications. And even though there's not a relevant attack yet, that we know of, we need to be prepared. So the CNSSP 15 defines that in the near term, in 2020, there will be basically fielded both traditional cryptography and post-quantum cryptography. And the objective is to complete the transition by 2035. Beginning January 2027, all acquisitions of equipment need to be PQC capable. And that's setting the foundation for the actual transition. By 2030, if it's not capable, it's got to be retired. So that's a hard stop for the national security systems. And then the CNSA algorithms will be mandated in 2030. So the protocol used by the December 3031, and the objective obviously is to complete by 2035. So how's that impact the TPM? So what the TPM has done is to define a subset of those CNSP crypto algorithms, and it's in version 185 of the TCG specification for the TPM, and that specification will be released this fall, and it will be supported ongoing for different rollouts. In for CLSQ in particular, we plan on supporting engineering samples by Q1 2026.
Eric, you want to add anything on this?
Yeah, Steve, that was a lot of acronym soup. No offense.
Yeah, sorry about that.
I'm going to try to help our readers get a few more pieces out of that. So CNSA is kind of the commercial arm of the National Security Agency, and NSA's charter for the U.S. So a lot of this is U.S. specific.
Right.
What you'll find that EMEA, Europe, lots of parts of Asia do tend to adopt what the U.S. does, particularly from the NIST standard side. So the federal government, using NSA kind of as its security arm, is saying to all critical infrastructure players, and you can read that as anybody that's doing cloud-based stuff is going to fall in that category. Anybody doing networking systems, anybody doing telecom, they all fall into this category. So all the stuff that Steve was saying is effectively the government saying, if you're providing any of this stuff, 2027 is your wake-up call. You need PQC. And 2030, you better have it all. And by 2035, we don't want to see any of the legacy PKI stuff. That's the ECC and RSA. So Steve did a great job of laying out all the standards that are going to drive this. But the root of this is the U.S. government, particularly NSA. And so I think the TCG, picking up on that, and I'm going to let Ari, he's got probably some very interesting insight on this too. But that 1.85 spec will be where TCG is now adding it, just like Steve was saying, to the TPM specification. And so you'll see other companies start to now add that into their TPM products, and also on the soft side, Ari, you want to add something to it?
Yeah, thanks, Eric. So, if you look at the beginning of, TPM implementations with 1.2 in, the late 90s, early 2000, they were implementing SHA-1 and RSA 1024, which are not trusted at all right now. So with TPM 2.0, they focused on, ECC and RSA. And so TPMs that are implemented to meet the standard today are using those algorithms. Obviously, moving forward, TPMs are going to have to support these new algorithms, and that's why it's good that TCG is defining that, so everybody does it the same way, and also a good reason to have FPGAs or other technologies that would allow you to make that change on the fly.
No, so that's a great point, Ari, and I would like to pick on that a little bit. And I think Eric mentioned about 4 billion TPMs already in use. So they are on the classical or, the current spec, which is non-PQC. So if you have a TPM in your system, FPGAs with PQC protection, that Lattice is planning on, they could be a very worthy companion in your system to give the PQC protection and also Root of Trust FPGA with PQC, CNSA mandated PQC algorithms could now cover all of the 5 roots of trust going forward, even with the TPM 1.85 established. So I think this synergy will continue, and the modern systems would need both systems. We are coming to the end of our discussion, so I would like to go around the table, and I would like you to give us some closing thoughts about the evolution of TPMs and their synergy with the components around them, and what does the future look like of secure systems. So I will start with Ari, and we'll go from there. Okay.
Thanks, Mamta. Yeah, so when people talk about TPMs these days, it's funny, they're just saying, hey, I need to add some hardware security thing. But they don't necessarily know what that means. They've just heard of it because there's billions of them out there. But in terms of going into the future, the key thing is TPMs need to start supporting these new capabilities, the new algorithms, as we've talked about, and new roots of trust around, update and those kinds of things. So everything's getting more and more sophisticated, and implementations of TPM and the standards are going to have to sort of continue to evolve. And I think that's what we'll see, in the coming years. Steve?
Yeah, so the evolution of the TPM it's spot on. It started with the PC and it's evolved. It started with the old algorithms. They've evolved to PQC. So what I see in that is the industry is evolving simultaneously, and the TPM is evolving with it. So the next trends. So if you look at what the next trends are in the industry, that would be a reflection of what the TPM needs to provide for security. And I think that would fall into 2 categories. First, AI, which is trusting all of the data that's used for training on the AIs. If you train an AI with incorrect data, just like you, if you listen to incorrect data, it changes the way you think. And AIs are no different. Their training data needs to be reliable. And so I think that first off, the AI training data reliability is going to play a big role. Also, again with AI, you've got personal agents or with agency for you personally, and how do you trust that agent has done the correct thing, and you didn't the agency that you gave it is got to be trusted as well. So that's another piece where the AI or the TPM is going to need to be able to cover some of those security aspects, as well as the personal identification things that go along with it. So I think, just to summarize, that the industry is going to point to how the TPM needs to evolve in going forward. And Eric, do you have anything to add to that?
Yeah. So Steve, you're speaking to my heart there with data provenance effectively.
Yeah.
I think, yeah, that's going to be a big deal. So I definitely think because of AI, being able to, for lack of a better way to put it, put trustworthy identity onto data itself. And a TPM will be a good tool for that. FPGAs can also be, because the speed at which that data could be coming in could find that the TPM is the credential, and something like an FPGA can watermark in real time that data faster and better than the TPM. Also, I think as we're talking about this evolution, TCG is now talking about cyber resilience. There's a cyber resilience working group. I represent Lattice on that work group. There is a guideline that came out from them now 2 summers ago. And I think that the evolution, and remember the topic at the beginning was TPMs and FPGAs to make secure systems. So I think what we're going to see is more dynamic capabilities in a security way, or let's call it a dynamic root of trust, for lack of a better way to put it, are going to become the future, because we need a lot more speed. The TPM on the credentialing, the attestation, the key vault, all that's excellent. And because of the base software that's out there, that doesn't, I don't think, go away. But the evolution of secure systems, I believe, is going to move more in this direction of having a dynamic component that gets more standardized. Whether that comes through TCG or just by the efforts in the industry, I think is yet to be determined. But the other thing, and I'll leave our readers with this, or I shouldn't say readers, our audience that's listening, I think it's an exciting time to be in security. The next 5 to 10 years, AI, everyone's focused on AI, they're missing the security implications of it. And so once that hits, and it usually hits in a very fast way, security in a dynamic way to help AI systems be trustworthy is going to be a big, big deal. Mamta?
Yeah, thank you. Thank you, our panelists, for sharing your expertise today. And thank you, everyone watching, for joining us in this important discussion. As we heard throughout the session, TPMs and Root of Trust FPGAs are complementary. Together, they deliver a strong hardware-based trust at the system level, enabling, credential storage, secure boot, attestation, and ultimately achieving long-term cyber resiliency. So I thank again our distinguished panelists, and to learn more, please visit us at latticesemi.com. Thank you.